Imagine walking into a familiar laboratory, shining a laser through a crystal, and believing you understand what you're doing. Day after day, scientists generate entangled photons to probe the mysteries of quantum mechanics, thinking they are merely producing twin particles whose properties are linked in ways that defy common sense. Now, imagine that hidden within this everyday experiment lies something far more extraordinary, a universe of patterns and structures that exist in 48 dimensions, each harboring thousands of distinct topological signatures. It is as if an invisible city of unimaginable complexity had been woven into the very fabric of the light itself, waiting patiently for someone to notice it. To grasp the significance of this, we first need to revisit the phenomenon of quantum entanglement, famously called spooky action at a distance by Einstein. Picture two dice, one in New York, one in Tokyo. Each time you roll one, the other magically shows the same result. This strange correlation mirrors what happens with entangled particles. Measure one property of one particle, and its twin instantly reflects a corresponding property, no matter how far apart they are. In laboratories, physicists create entangled photons using a process called spontaneous parametric downconversion, SPDC, where a single photon entering a crystal splits into two twin photons with correlated properties. These twins have been central to decades of experiments, forming the backbone of quantum communication and foundational tests of quantum mechanics. Yet, despite the countless experiments conducted, no one had noticed that the spatial arrangement of these photons conceals an entire hidden structure, a topological universe encoded in the very twists and turns of light itself. It is much like discovering that a painting you have seen every day contains a secret image beneath the surface, revealed only when viewed under the right light or with a special filter. The entangled photons, familiar to generations of physicists, were quietly carrying this hidden world all along, a world whose discovery could change how we think about storing and transmitting quantum information. The excitement is not merely aesthetic. It's the realization that nature has provided the resources for robust quantum information encoding, and we are only just learning to read its blueprint. The key to unlocking this hidden universe lies in a property of light known as orbital angular momentum, OEM. Unlike polarization, which can be thought of as simply up or down, OEM describes a twisting or corkscrew-like motion of light as it travels. Imagine a tornado spiraling through the sky, with a dark center and whirling energy around it. Each twist represents a distinct quantum state, and unlike polarization, these twists can exist in an effectively limitless number of configurations. When photons are entangled, these twisting patterns themselves become linked, creating a multidimensional tapestry that scientists are only beginning to map. Here is where topology enters the story. Topology is the mathematics of connectivity. It's less about precise shapes and more about how objects are fundamentally linked. Consider the classic example of a coffee mug and a donut. Despite appearances, they are topologically identical because each has one hole. A mug can, in theory, be deformed into a donut without tearing it. In photons, topology manifests not in tangible objects, but in the relationships between quantum states, the way different twisting configurations connect, overlap, and protect one another. These structures are inherently robust, meaning that minor disturbances cannot easily destroy the information they encode. To illustrate, think of writing a message in sand on a beach. A small wave can wash it away in an instant. Now imagine carving that same message into a block of stone. No amount of small disturbances will erase it. This is essentially what topology offers to quantum information, a natural resilience. Until now, scientists believed that creating topological structures required multiple particle properties, such as OEM combined with polarization. This research shattered that assumption, showing that orbital angular momentum alone is sufficient to generate high-dimensional, robust topological structures. The result is a previously hidden, extraordinarily rich landscape embedded in light itself, accessible with tools that scientists have already been using for decades. As the researchers began to study the correlations between these twisting photons, they realized that the entangled system behaves as if it exists in 48 dimensions. This does not mean our universe suddenly has 48 directions like up, down, left, right, and so on, but rather that the mathematical space needed to describe the system fully requires 48 independent parameters. Imagine a highly advanced control panel in a recording studio. A simple stereo system might have 3 knobs for volume, bass, and treble, but a professional mixer could have dozens, each controlling a different aspect of the sound. Each knob adds a new dimension to the system. Similarly, the 48-dimensional space of entangled OEM photons captures the full complexity of their topological relationships, a multidimensional landscape previously hidden in plain sight. Within this space, the researchers identified over 17,000 unique topological signatures, each one like a knot intricately woven into the fabric of light itself. These high-dimensional patterns are not just abstract mathematics. They define pathways for information to flow and interact in a manner that is resistant to noise and disruption. The higher dimensional nature of the system allows for qudits, quantum units with multiple states, vastly increasing the information-carrying capacity beyond traditional qubits. Yet these high-dimensional states are usually fragile, like threads in a delicate tapestry, prone to unraveling at the slightest disturbance. Topology, however, transforms this tapestry into a structurally resilient fabric, ensuring that even if part of the system is perturbed, the overall information remains intact. It is akin to encoding a secret in the weave of a complex rug rather than in a single fragile thread. The most remarkable aspect of this discovery is its immediate accessibility. The tools required to observe these topological structures are already present in many laboratories around the world. What was missing was the perspective to recognize the hidden structures. By combining experimental observation with insights from quantum field theory, the researchers could predict where and how to look for these topologies, and their measurements confirmed their existence. This synergy of theory and experiment reveals a powerful new framework for quantum information, one that is naturally robust and capable of operating outside idealized laboratory conditions. The implications are profound. Quantum communication, computing, and sensing all struggle with the fragility of quantum states. Topological structures embedded in entangled light could serve as a built-in shield, providing robust error correction and stability, which are essential for real-world quantum technologies. This discovery also illustrates a broader truth about science. Sometimes the most profound structures are hiding in plain sight, patiently waiting for us to recognize them. Just as explorers uncover hidden ecosystems beneath the familiar landscape or notice intricate patterns in a simple ripple on the water, physicists have found that entangled photons carry within them a multidimensional universe, a secret topological world capable of transforming the future of quantum technology. By learning to read this geometry, we are not merely observing quantum phenomena. We are unlocking a new language of nature, one that could enable secure communication, fault-tolerant quantum computing, and a deeper understanding of the very structures underlying reality itself. Light, it seems, has always been more than energy or illumination. It is a carrier of hidden worlds, waiting for the human mind to see its true form.